Don't know. Okay, great. Perfect. So I wanted to start with you looking at sample problem 4.20, identifying the type of redox reaction that's occurring. You might remember that last class we talked about decomposition, combination reaction, displacement reactions, single displacement, double displacement, and combustion reactions. Classify each of the following redox reactions as a combination, decomposition, or displacement reaction. Write a balanced molecular equation for each, as well as total and net ionic equations for part C, and identify the oxidizing and reducing agents. We're going to start, of course, with A. Magnesium plus nitrogen gives us magnesium nitride. Well, here is a great question that we're going to have to employ a little bit of our nomenclature knowledge. Okay, so let's see here. If we have magnesium, which is a solid, we know that the elemental symbol for magnesium is Mg, and it's a solid, and we're adding that to nitrogen. Nitrogen is a diatomic molecule, which we learned earlier on in the class, and then we're making magnesium nitride. Now, what kind of charge does magnesium like to adopt? Magnesium likes to have a 2+ charge because it is in group 2A. Nitrogen is in group 5A. It likes to gain 3 electrons to have a 3- charge so that it can be isoelectronic with neon. And so when we combine those two, the kind of, what is it, the Dr. Silverberg version is you switch these numbers like that, so you get Mg3N2. Anyhow, whatever you need to do works for me. So we have magnesium nitride like that, and magnesium nitride is a solid. Now we're going to identify this as being a combination, decomposition, or displacement reaction. Who could identify this one for me? And I guarantee that all my students could identify this. How would you best classify this reaction? Would you say, yeah, absolutely. Thanks, Joey. It's a combination reaction. So yeah, it's not composition. We have decomposition and we have combination. So this is a combination reaction because we're combining 2 reactants. So this is a combination reaction. Okay, now let's identify the oxidation states. Remember that when we have an element in its pure form, the oxidation state is 0. And so we have a 0 for our magnesium and a 0 for our nitrogen. You know what I just noticed? I haven't balanced this equation, so I should do that before I move on. In my product, I have 3 magnesiums, so I'll put this there, and I have 2 nitrogens. So there we go. I balanced the equation. Now, if we look at the magnesium nitride, okay, this ionic compound, which is composed of a metal, magnesium, and a non-metal, nitrogen, what's the oxidation number, or the oxidation number of the magnesium? Well, again, magnesium is in group 2A, so it's got an oxidation number of +2. What's the oxidation number of the nitrogen? Well, for a non-metal, I can figure that out based off of the charge of my cation. I have an oxidation number of +2 for my magnesium, and there's 3 of those. So that gives me a +6. That means that my nitrogen overall has to have a charge of -6, and then I have 2 of them. So that means the oxidation number for the 2 nitrogens are both going to be -3. All right, so now we have the oxidation numbers identified for all the elements in their free state and the elements in the ionic compound. So let's determine who's being oxidized and who's being reduced. Well, you can see that the magnesium goes from 0 to +2, and so it is being oxidized, right? Remember, oxidation is losing electrons, and so when we go from 0 to +2, that means we're losing negative, right? We're losing a negative charge, and electrons are negative, and so this is oxidation. The nitrogen is going from 0 to -3. Remember, reduction is gaining electrons, so this is losing or gaining electrons, and so since we go from 0 to -3, this is reduction, so oxidation and reduction. And so now we've identified this as a combination reaction, and we've identified the magnesium is undergoing oxidation, but we knew that because metals tend to lose an electron, or tend to lose electrons, and they undergo oxidation, and non-metals tend to be reduced. Now let's identify the oxidizing and reducing agents. And so since magnesium is undergoing oxidation, it is the reducing agent because it's causing the nitrogen to be reduced, and the nitrogen is the oxidizing agent because it's causing the magnesium to be oxidized. Give me a thumbs up if you follow me on that one. The first one. All right, good. Good. Just going to move this up here, because I can see already I'm going to run out of space on this slide, aren't I? Yay. There we go. Okay, let's try the next one. It deals with hydrogen peroxide. So let me just create some space here. So we have hydrogen peroxide. This was A. This is B. We have hydrogen peroxide, which is a liquid. And it is being converted into water and oxygen gas. First thing I should do is balance out this equation. Let's see, I have 2 oxygens. And, you know, if you just put a 1/2 here, that would balance out the entire equation, wouldn't it? But then if I want to get rid of that fraction, I would multiply everything by 2. So I'd have a 2 and a 2 here, and 1/2 times 2 gives you 1. So there you go. There's my balanced equation. Now, you might remember that hydrogen always has an oxidation number, or usually has an oxidation number of +1 unless it's combined with a metal. Oxygen is not a metal. And you probably also remember that oxygen usually has a charge or an oxidation number of -2 unless it is in a peroxide. In this case, who can tell me what the oxidation number of oxygen is in hydrogen peroxide? Yeah, absolutely. Pardon me. I see that Aaron has the right answer. It's -1, as does Ashlyn and Gabrielle. All of you are correct. The answer is -1 for the oxidation number. If we look at the pure oxygen that I have circled in blue, who can tell me what the oxidation number of pure oxygen is? Not a trick question. There you go. It's 0. Absolutely. Mr. Dion hates trick questions. Now, if we look at the oxidation numbers of the hydrogen and the oxygen in water, the hydrogen is +1 because it's combined with oxygen, which is not a metal, and the oxygen in this case is -2. And now we can identify what's undergoing oxidation and what is being reduced. And we can see that the oxygen is undergoing reduction here as it goes from -1 to -2. And so it's undergoing reduction. Well, what else do we know about that oxygen? It's also undergoing oxidation. Okay, so this is oxidation like that. So what does that tell us? If the hydrogen peroxide is supplying the oxygen that is both undergoing oxidation and reduction, that tells us that the hydrogen peroxide, the H2O2, is both the oxidizing and reducing agent. Okay, so H2O2 is both, maybe I should put both oxidizing and the reducing agent. Now, who could identify the type of reaction? I haven't asked you that yet. Would this be considered a combination, decomposition, or a displacement reaction? What do you think would be the best answer there? Yeah, absolutely. I see that my students are writing decomp. Yeah, decomposition, and you are absolutely correct. This is a decomposition reaction. Okay, a decomposition reaction. And the last one, I'm gonna just go over the solution here. The last one is, what was the question? I didn't even read it. It's when we take aluminum, and we can just scribble it in here quickly. Aluminum, which is a solid, and then we add it to lead-2 nitrate, so that's PbNO3, 2 aqueous, and then we produce aluminum nitrate, which would be AlNO3, 3 aqueous, plus lead, solid lead like that. Then we have to balance the equation. So fix my PB, that doesn't look very good. So there, is that balanced? Nope, there we go. So now I've balanced the equation. So what we're gonna do is we're gonna take that balanced equation and we break it apart into its ions. Let me rewrite the equation here for you. So the balanced equation was, where it was 2 aluminums solid plus 3 lead-2 nitrates, which is aqueous, which produces 3 leads. This is solid plus 2 aluminum nitrate aqueous like that. Okay, so that's the overall reaction. Can anybody, I guess the answer is here. So this is a displacement reaction, right? Because the aluminum is displacing the lead from the lead to nitrate. I'll just go over the oxidation numbers kind of quickly here. The oxidation number of the aluminum is 0. Over here, the lead is 0. The oxidation number of the lead in lead 2 nitrate is +2. For the aluminum nitrate, it's +3, like that. And so you can clearly see that in nitrate, it's nothing's going to change in the nitrate. So what's being oxidized and what's being reduced? Well, aluminum is being oxidized because it's going from 0 to +3. So this is oxidation. And the lead is undergoing reduction because it's going from +2 to 0. So this is undergoing reduction. Here's the net ionic equation where the total ionic equation where everything is broken apart into its ions. And the net ionic equation is where we cross out the nitrates and we just write overall what's happening here. And so since the lead is being reduced, that would mean that the aluminum is the reducing agent. And since the aluminum is undergoing oxidation, the lead would be the oxidizing, and the lead 2+ would be the oxidizing agent, like that. All right. The last part of chapter 4 is section 4.7. We're going to skip that part entirely, so you can just skip section 4.7. I'm never going to ask you about anything in that section. Well, with that in mind, let's take a look at some practice problems from our textbook. If you're ever at a loss and you need more practice, where do you go? The textbook. You're paying for it. It's got all kinds of problems in it, and it has the answers to problems. And so I chose some questions from the back of the book. I posted an announcement. Hopefully you've all had a chance to take a look at these problems. Let's start with 4.26. How many moles, how many ions of each type are present in each of the following? Well, I just have one here. We have 130 milliliters of 0.4 molar aluminum chloride. Aluminum chloride is an ionic compound, isn't it? Because the formula of aluminum chloride is AlCl3. It's made from a metal, aluminum, and a non-metal, chlorine. And so if we take aluminum chloride, okay, and we have an aqueous solution of it, since it's ionic, it's going to break apart into its ions. The aluminum is in group 3A. It's going to have a 3+ charge. And we're going to have 3 chlorides. Chloride has a -1 charge, right, because it's in group 7A. It gains 1 electron to become isoelectronic with argon. Now, we want to know how many moles of each of these ions, right? We want to know the number of moles of aluminum. We want to know the number of moles of chloride. Okay. And we want to know the number of ions for each of these. Okay. Well, if we know the number of moles, we know that there's 6.022 times 10 to the 23 ions in a mole. And so we could just use Avogadro's number to solve for that. Well, how many moles of aluminum chloride am I starting out with? I've been given the volume of a solution, right? Here's my volume, and I've been given the molarity, right? We know that molarity is equal to the number of moles per liter, or N over V. Since I have big M and I have V, I can solve for N because I know that N is going to be equal to big M times V. So if I want to get the number of moles of aluminum chloride, aluminum chloride, I'm going to take my volume. I'm going to convert this into liters in my head, so divide by 1,000. So I have 0.130 liters times 0.45 moles per liter. Okay. You see the liters are going to cancel out. I end up with the number of moles of aluminum chloride, and that is equal to 0.059 moles. 0.059 moles of aluminum chloride. Give me a thumbs up if you follow me thus far, and stop me if you have a question. All we've done is written the balanced equation for the dissociation of aluminum chloride, which is ionic. And now we know how many moles of aluminum chloride that we're starting out with. Well, if I want to figure out the number of moles of aluminum, where would I start there? I know that I have 0.059 moles of aluminum chloride. And from my balanced equation, I know that for every 1 mole of aluminum chloride, I have 1 mole of aluminum ions. Moles of aluminum chloride are going to cancel out, and I'm going to end up with the number of moles of aluminum. And the number of moles of aluminum is going to be 0.059 moles of Al3 plus. All right, so I've got that part. So now I know the number of moles of my aluminum. So first part complete. I wanted to determine the number of moles of chloride ions. Okay, I have 0.059 moles of aluminum chloride. And I know that for every 1 mole of aluminum chloride, it dissociates, I form 3 moles of chloride ions. I'll look again. Moles of aluminum chloride cancel out, and I'm left over with the number of moles of chloride ions, which is equal to 0.177 moles of chloride. Now I've solved the second part. It's asking, so we've done this part, we know the number of moles. Now we want to know the number of ions. For that, it's just going to take a little more dimensional analysis. I know that if I have this many moles of aluminum ions, and I know that in 1 mole of Al3 plus, I have 6.022 times 10 to the 23 Al3 plus ions. Okay, you can see that moles of aluminum 3 plus are going to cancel out, and I end up with the number of ions. Now, did I calculate that? I did. And you end up with 3.6 times 10 to the 22 ions of Al3 plus. We can do the exact same process for our chloride. We know that in 1 mole of chloride, we have 6.022 times 10 to the 23 chloride ions. We multiply that spinach out, and we get 1, well, that's not what it's doing. We get 1.1 times 10 to the 23 ions of Cl minus. All right, and there we go. Not to harp on what we were talking about earlier as a group before the lecture actually began, but remember, you know, what kind of math is being done on this in this problem? Multiplication and division. And you all are allowed to bring a scientific calculator into the examination room. So that means that there's no mathematical operation in this problem that anybody in our class cannot do. What's the difficult part? It's being able to read the problem and interpret what's going on. I'd say another thing that may be kind of still tricky for some people is, in order for you to, master the content at this point in the class, you've got to be rock solid. I mean, rock solid on nomenclature, and know what aluminum chloride is. Know that aluminum is a metal. Know that chlorine is a non-metal. Know that it's ionic. Know it's going to dissociate. You got to know how to put the charge for an aluminum because it's in group 3A. You got to know that the charge on a halogen when it becomes a halide is going to be -1. Okay? By now, we assume that you don't have to think too hard about those things. All right, let's move on. Let's try this question, 4.43. Hey, this question says, when each of the following pairs, and there's only one, of aqueous solutions is mixed, does a precipitation reaction occur? If so, write balanced molecular total ionic and net ionic equations. I'm going to assume that at least one person who's hearing the sound of my voice tried these problems before coming to class. Can anybody tell me, is there a precipitate formed? And could you tell me just what it is for the people who did the problems ahead of time? You can write the formula or write the name. Who tried this problem? Yeah, absolutely. Thanks, Violet. Yeah, the answer is silver bromide. There is a precipitate, right? Violet, did you have to look in the solubility table or do you have it memorized? Yeah, awesome. Okay, great. So she said she memorized it. Remember, I always give you part of the solubility table, and then you only had to have what, memorize the first couple rules or something. Anyhow, so we're starting it with ammonium bromide. So that means, again, we've got to be very confident in our nomenclature. And ammonium is NH4, it has a charge of +1. And so it's going to combine in a 1-to-1 ratio with bromide. That's an aqueous solution, right? It tells you that it's a pair of aqueous solutions, so we don't even have to look at the solubility table. Plus silver nitrate. Silver only ever has one oxidation number or oxidation state. It's only ever +1. It is not like the other transition metals like copper or cobalt or manganese or chromium that can adopt more than one charge. It's always +1. Nitrate is always -1. And so silver nitrate is AgNO3 and it is aqueous. So what's going to happen here is we're going to swap those ions, right? This cation is going to combine with this anion. And this cation is going to combine with that anion. All right, and when we do that, we end up with silver. We end up with, let's write ammonium nitrate first, okay, which is a very soluble compound. And then, as Violet said, you could look it up in the solubility table, or you could memorize the silver bromide is a solid. And so the answer is yes, a precipitate will form. And this is our molecular equation. I have another question for you. Is this molecular equation balanced? Is it balanced the way it's written? Yay or nay? Or no? Yes, it's absolutely balanced. So there's our molecular equation. Now we're going to write out our net ionic equation. That means we're going to break everything apart into its ions. What do we break apart into its ions? Anything with AQ is broken into ions. Okay, so we have ammonium bromide. We're going to break that into ammonium. We're going to write AQ after that, plus bromide. We're going to write AQ after that. Silver nitrate is aqueous. We have silver plus aqueous plus nitrate. Aqueous, it produces ammonium nitrate. So we'll put NH4 aqueous plus nitrate. Aqueous. Now, since silver bromide is a solid, we leave it as it is, AgBrS. Now, in the, oh, sorry, that wasn't the net ionic equation, that's the total ionic equation. In the net ionic equation, we're going to remove spectator ions. That means that anything that's the same in the products and the reactants, we can eliminate. So ammonium is the same on both sides, as is nitrate. And now we're going to write the net ionic equation, which is going to be silver plus bromide produces silver bromide solid. All right, completely legitimate question for the final exam, or any exam really in this class. Okay, we've covered molecular equations, total ionic equations, net ionic equations. All right. Well, let's take a look at another problem. Is anybody else enjoying this? Just me? Okay, question 4.72. If we take 26.25 milliliters of a 0.1850 molar sodium hydroxide solution, and it reacts with 25 milliliters of sulfuric acid, what's the molarity of the acid solution? Right? What's molarity? Okay, molarity, big M, is the number of moles per liter, right? N over V. If we want to figure out the molarity of the sulfuric acid, what we need to know is the number of moles of sulfuric acid, okay? And then we're going to divide that by the volume of the sulfuric acid. We've been given the volume of the sulfuric acid, right? This is equal to 0.02500 liters. All I did was divide that by 1,000. So let's put that in here, 0.02500 liters. So now what's the problem? The problem is figuring out how many moles of sulfuric acid are there. If we know that, then we can just divide that by 0.025 and we're done. Plug it in the calculator and go home, right? What's the tricky part then? The tricky part is knowing that when you combine sodium hydroxide, which is a strong base, it's an electrolyte, it's an aqueous solution, and we combine that with sulfuric acid, we end up doing a neutralization reaction. What are the products of the neutralization reaction? Well, when we take a base and we combine it with an acid, we usually end up with a salt plus water. The salt that we end up with is not table salt. It's not sodium chloride. There's no chlorine in here. But we do end up with a salt. Right? The salt is made up of a metal and a non-metal. The metal in this case will be sodium. Okay? And it's going to be combined with sulfate. We're going to end up with sodium sulfate. But what's the charge on a sulfate? A sulfate is SO4 minus. So that means since sodium is +1, we would need 2 sodiums to make sodium sulfate, which is a soluble compound, plus H2O. Now, is this a balanced equation? The answer is no. We have 2 sodiums and sodium sulfate, so we need to at least have a 2 here. We have 1 sulfur, and so now, oh, we don't have enough oxygens, do we? Have 6, 4, there we go. And our hydrogens, now we have 4 hydrogens and 4 hydrogens. So now the equation is balanced. So what's the stoichiometric ratio of sodium hydroxide to sulfuric acid? The ratio is for every 2 moles of sodium hydroxide, I consume 1 mole of sulfuric acid. We leave this stoichiometric coefficient out. It's assumed, and we're going to need that to figure out how many moles of sulfuric acid we have. Because we're starting with 26.25 mils of sodium hydroxide. We know that there are 1,000 milliliters in 1 liter. We know the concentration of our sodium hydroxide, which is 0.1850 moles of sodium hydroxide in 1 liter of sodium hydroxide. If I stopped right here, what have I canceled? Milliliters, sodium hydroxide, and liters. If I stopped right here, all I would have is the number of moles of sodium hydroxide. But from my balanced equation, I know that for every 2 moles of sodium hydroxide that's consumed, I consumed 1 mole of sulfuric acid. Look at this. Look at this. Now, if we were to stop, we would have the number of moles of sulfuric acid. Let's punch all that spinach into our calculator, and when we do, we end up with 0.002428 moles of H2SO4. So when we want to calculate the molarity of our H2SO4, it's going to be equal to 0.002428 moles divided by 0.02500 liters. When we divide that, we get the concentration of our sulfuric acid, which is 0.09712 molar, like that. Again, nothing more than multiplication and division. What's the trickiest part? Interpreting the problem and being able to come up with the balanced equation. Because even if you knew that sulfuric acid plus sodium hydroxide gives you a salt plus water, if you didn't balance the equation correctly, you would not have this conversion factor, and your answer would have been off by a factor of 2. Okay? All right, give me a thumbs up if that helps. Think, I'm getting it. All right. All right, good. Practice never hurts. You know, as we were saying, or as we were talking about as a group earlier, taking the leap from not having the textbook to rely on, not having, cheat notes, and I don't mean cheating like literally cheating, but not having some cheat notes with you, it takes guts. It's a leap of faith. You have to trust yourself and you have to be willing to make some mistakes along the way. Okay, well, I can promise you that on your final exam, I'm definitely going to ask you something, or the ACS will ask you something about oxidation number, okay? Oxidation number always comes up on exams, and let's take a look at this and see if we can help master our oxidation number prowess. The first one is difluoro, so it would be dichloro-difluoromethane, and you have CF2Cl2. Well, let me draw it over here, CF2Cl2. The oxidation number of the halogens is always -1, right? Unless they're just combined together. If you have a halogen combined with another halogen, those are all -1. So I have -1 times 2 here, and I have -1 times 2 here. If I tally all that up, I get a total of -4. So that means that the oxidation number on my carbon must be +4 in order to neutralize or balance out the oxidation states of the 4 halogens. Okay, so let's look at the next one, which is sodium oxalate. This one here, sodium oxalate. So Na2C2O4. Well, sodium is in group 1A, and thus it's going to have an oxidation state of +1. Now, if there's 2 of them, that gives me an overall charge of -2. So that means that the oxalate ion, the C2O4, must have a charge of 2-. The oxidation number of oxygen is -2 unless it's in a peroxide, and I have 4 of those. -2 times 4 gives me -8. Now, -8 plus something, okay, gives us -2. What could that something be? And the answer is what? Who could tell me? -8 plus what gives you -2? +6, absolutely. So this is +6. Now, if I have +6, but there's 2 carbons, that means that that oxidation number, that charge is going to be divided over 2. So that means it's going to be equal to +3. So the oxidation number of the carbon here is +3. Okay. And kind of running out of space here. Note to self: make more room on slide. Okay, I'll draw a line here. See if that'll clear up some space. The next one is the bicarbonate ion, or the hydrogen carbonate ion. So we have HCO3 minus. The oxidation number of our hydrogen is +1. So that tells us that CO3 overall, the carbonate, has an oxidation, or sorry, has a charge of 2-. Oxygen has an oxidation state of -2 times 3. That gives me -6. -6 plus something equals -2, right? Gives me this 2- charge. The answer is what? So we're going to scroll. Thanks, Ashlyn. The answer is +4. And so the oxidation state of our carbon is +4. And bicarbonate, maybe I'll just put it here +4, like that. -2 for the oxygen, whatever. Anyhow, I'm really ruining the space here, aren't I? We'll move this one up here, and then there we go. Now we've got all kinds of room to solve the last one, which is C2H6. This is ethane. Well, the oxidation number of hydrogen is always +1 unless it's combined with a metal, and carbon is not a metal, it's a non-metal. So we have +1, nope, getting ahead of myself, +1 times 6, that gives me +6. So that means that this side must be -6 overall, but there are 2 carbons, so that means that the oxidation number of the carbon must be -3. So -3. All right, give me a thumbs up if that helps you with some oxidation numbers. Cha or no? Okay. Well, if it helps you so much, and I hope it does, tell me what's the oxidation number of carbon in carbon dioxide. I'll give you a second to look at it. First person to get the answer, just, yeah, good. It's +4. Absolutely, +4. Why? Because oxygen always has an oxidation number of -2, unless it's in a peroxide. So we have -2, and then we have -2 times 2, which gives us -4. So that means that this one must be +4. There you have it, folks. Good. A little more mastery of oxidation number. 4.94, identify the oxidizing and reducing agents in the following reactions. Again, here's that little A icon. When you see that icon in the back of the textbook, it gives you the answer. So you'll know whether you're right or whether you're wrong. Okay, let's see here. I don't like this reaction written out like this. I need more space to think. Let me rewrite the reaction, and while I'm doing that, you can try to identify who's being oxidized and who's being reduced. Now, in order for you to solve this problem, you got to be pretty quick with your assigning oxidation numbers, or it would take you all day, to solve this. The proton, right, H plus, that obviously has an oxidation number of +1. Chloride obviously has an oxidation number of -1. Tin is in its purest form, or pure form, it's 0. Now, if we examine the nitrate, the oxygen has an oxidation number of -2 times 3 is -6. What plus -6 gives me -1? The answer is +5. So we have a +5 for our nitrogen and a -2 for our oxygen. We look at SnCl6, 2-. The oxidation number of the chloride is going to be -1. And we have 6 of those, so -1 times 6 gives me -6. What plus -6 gives me a 2- charge? The answer is +4. So my tin is going to have an oxidation number of +4. Number 4 looks like crap. There we go. Then we have nitrogen dioxide. Oxygen has an oxidation number of -2. There's 2 of those, so -2 times 2 is -4. The oxidation number of the nitrogen is +4. Then in the water, oxidation number of oxygen is -2. Hydrogen is +1. There we have it, folks. We've identified the oxidation numbers of everything, all the players in here. Now we can see who's being oxidized and who is being reduced. Well, let's see here. We see that the tin is going from 0 to +4, right? Remember, oxidation is losing electrons, and so the tin is being oxidized. Okay? If it's being oxidized, that means that it is the reducing agent. And if you're like, well, you haven't even identified if something's being reduced. Well, I can tell you right now that if something's being oxidized, something else has to be undergoing reduction. Who could tell me what's being reduced? What is being reduced in this problem? It's not chlorine, because the oxidation number of the chlorine isn't changing. It's going from -1 to -1, so that's not a change. Yes, the answer is the nitrogen. The nitrogen is going from +5, right? The nitrogen here is +5, and over here it's +4. That means it's gaining electrons, right? It gained 1 electron, and so it's undergoing reduction. The reduction is gaining electrons. And so that tells us that the nitrogen is undergoing reduction, and the oxidizing agent would be the nitrate. So oxidizing agent. All right, there we go. A little practice on oxidation and reduction. Again, you can see how you're going to be pretty quick on your oxidation numbers. Otherwise, it would just take you years to solve that kind of problem. And let's see, what other problems did I have here? 1.107, let's give this one a try. Predict the products and write a balanced equation for each of the following redox reactions. Let's go over these. I'm going to show you how quick I think you should be able to solve these. I am not a speed guy. Okay, don't ever think that Mr. Dion's thinking about timing you or stopwatches. Of course, we have to put time limits on exams, but I think they're pretty generous. But I think you should be able to look at A and say, okay, I'm taking strontium, which is in group 2A. It's a metal, and I'm combining it with bromine, which is a halogen. It's a diatomic molecule. So I have a metal, right, and a non-metal. Well, I'm going to combine that metal and non-metal to make an ionic compound. Strontium is in group 2A. It's going to want to have a charge of 2+. Bromine is going to want to have a charge of -1, so bromide. So I'm going to have SrBr2. Like that. That's it. So strontium bromide, and since it's ionic, it's going to be a solid. That's it. Is the equation balanced? Absolutely. The strontium is going from 0, and the bromine is 0. The strontium is +2 oxidation state, and here the bromine is -1, so the strontium is undergoing oxidation, and the bromine is undergoing reduction. The next one, B, we have silver oxide. It's undergoing decomposition. What's it going to make? It's going to make silver, which is a solid metal, and oxygen, which is a gas. We need to balance that out. So if we put a 2 here and a 4 here, it's balanced. There we have it. We know the oxidation number of the silver and the oxygen are both 0 because they're in their pure form here. It's +1 in silver oxide. Sorry, silver is +1 in silver oxide. The oxygen is -2. And so the silver is undergoing reduction, and the oxygen is undergoing oxidation. Yeah. The next one is manganese. So we have in C, we have manganese, which is a solid metal, plus copper nitrate. Well, you can see that you have a pure metal being combined with an aqueous solution. So this is, if there's any reaction at all, it would have to be a single displacement. I would never ask you this question, actually, now that I look at it. I could ask you what's being oxidized and reduced if I gave you the product, because I wouldn't expect you to know that you're going to form manganese 2 nitrate. That's beyond the scope of our course. So again, if I provided you with this equation that I just wrote here, and I said, okay, what's being oxidized, what's being reduced, that I would expect you to be able to figure out, okay? The first two, sure, I'd expect you to be able to give me the products. But so let's write down the oxidation numbers. My manganese is going to be 0 in the pure form. Copper is going to be 0. Here in my copper nitrate, nitrate has a charge of -1. There's 2 of them, so it's copper 2 nitrate. And here I have manganese 2 nitrate. You can see that the manganese is undergoing oxidation and the copper is undergoing reduction. Like that. All right, last problem that I picked up from the book. It's a limiting reactant problem. Who wants to try a limiting reactant problem? It's always good to do some practice on limiting reactants. They just don't go away, right? Okay. Let's see here. What do we got? In a combination reaction, 1.62 grams of lithium is mixed with 6.50 grams of oxygen. Which reactant is present in excess, and how many moles of product do you get? Okay, we're taking lithium, which is a metal, so it's a solid, and we're combining it with oxygen. And what are we going to get? We're going to get lithium oxide because we're combining a metal and a non-metal. What's the formula for lithium oxide? Well, lithium, it's in group 1A. It wants to have a charge of +1. And oxygen is going to want to have a charge of -2 because it's in group 6A. We have lithium oxide, and that is a solid compound. You see the oxidation number is 0 and 0, plus 1 minus 2. Anyhow, that's not what it's asking us about. It's telling us that we're taking 1.62 grams of lithium and we're combining it with 6.50 grams of oxygen. And it's asking us, which reactant is present in excess and how much lithium oxide do we produce. Let's solve the problem starting with our lithium and see how many moles of product we would get. We have 1.62 grams of lithium, and we know that in 1 mole of lithium, and this is going off of the periodic table, we have 6.941 grams of lithium. Now, is our equation balanced? I didn't even check that out. I'm such a bozo. Okay, 1 lithium, so 2 there, and then a half, so that would be 4 and 2. Okay, so now I have a balanced equation, and I see that for every 4 moles of lithium, I form 2 moles of lithium oxide. Now let's check here. Grams of lithium cancel, moles of lithium cancel. And I'm left over with the number of moles of lithium oxide, which would be 0.117 moles of Li2O. Let's do the exact same thing for our oxygen. We have 6.50 grams of oxygen. I know that in 1 mole of oxygen, I have 32.00 grams of oxygen, and I know that in when I consume 1 mole of oxygen, I form 2 moles of lithium oxide. Double check my units. These cancel, this cancels, and I'm left over with the number of moles of lithium oxide, which would be 0.406 moles of lithium oxide. So who could tell me what is the limiting reactant? Not which one is in excess, which one is the limiting reactant? Lithium or oxygen? Yes. The lithium is the limiting reactant, right? Smaller amount of lithium oxide. Therefore, lithium is limiting reactant. If the lithium is the limiting reactant, that tells us that O2 is in excess. How many moles of the product are going to be formed? Well, we're going to end up forming 0.117 moles of lithium oxide.